Okay, so we started with this as a warm-up. I gave you this rational function here, and I asked you to find f of 0. And as most of you found, if you plug in x equals 0, you end up with no solution. This is undefined. Again, the reason I put this in there is to remind us that when we solve for x equals 0, what we're actually finding is the y-intercept. And so since there is no solution here, it means that this function has no y-intercept. All right. So the next thing I asked you to find was x when f of x equals 0. So this is setting the function equal to 0 and then solving for x. And again, the reason I asked you to do this one is because this is finding the x-intercept. And I also wanted you to notice that when you set a rational function equal to 0, what happens is the denominator, once you multiply that to both sides, sorry, that should be a minus there. Once you multiply that to both sides, it's going to multiply by the 0 here, which means it will then be 0. So when you are doing these and you are trying to find the x-intercept, you don't need to spend time looking at the denominator. All of it should come from the numerator only. Okay, so since that's the case, I'll just take the numerator. X squared minus 4x plus 3 is equal to 0, which then factors into x minus 3, x minus 1 equals 0, and then giving us x equals 3 and 1. So those are our two x-intercepts, or the points 3, 0 and 1, 0. Okay. The next thing I asked you for was to find x when f of x is 1. And again, this is just setting y equal to 1, not 0. So if I have 1 for my y and I multiply the denominator over, I end up getting x squared minus 6x is equal to x squared minus 4x plus 3. And then it's just solving for x. Those two x squares will cancel each other out. I end up with a 2x over here, a negative 3 over here. So x is equal to negative 3 over 2. So again, this is just the coordinate set, negative 3 over 2, 1. Okay. And why I asked you to find this one will make more sense as we look into the actual lesson. Okay, the last piece was just to state the domain in interval notation. Again, if you go back to the domain and we look at the original denominator, we can see that x could not be 0 and x cannot be 6. So in interval notation, that means we're going to go from negative infinity to 0, and pick up again from 0 to 6, and then pick up again from 6 to positive infinity. Okay, so this was done sort of in preparation for our lesson today, okay, which is the graphing of rational functions. All right, so this part you guys have already seen this. A rational function is just a function in this form where we've got, it's basically a fraction, and we have an expression in both the numerator and the denominator. We've already talked about the denominator cannot be equal to 0. The domain of these rational functions we have also talked about. Anything or any value of x that would make the denominator equal 0 is not in the domain. It is a restriction on the domain. So we're going to start with this basic rational function, 1 over x. And so because the x is in the denominator, we know we can't divide by 0, therefore x cannot be 0. Again, just putting that into interval notation means going negative infinity to 0, picking up again 0 to infinity. Okay, so when we are looking at the graphs of these rational functions, we need to pay close attention to what is happening when we get close to these x values that are not in the domain. Okay? So again, I'm starting with this basic function here, 1 over x. Okay. So again, 0 is not in the domain, and so we want to figure out what is happening to our graph when we get close to 0 from both the left side and what's happening on the right side as we go away from 0. So starting with this little investigation here, I have a table, just a little XY table, where we're going to try some values. Okay, so in our first one, if I let x equals -3, when I plug that into the function, that gives me -1 over 3. So I'm going to go ahead and plot that point, -3 and then -1/3, which is about right there. If I plug in -2, I get 1 over -2, so that's -1/2. So -2, -1/2. If I plug in -1, I'm going to get 1 over -1, which is -1. Let me plot that there. If I let x be -0.5, that's going to give me -2. So I have -0.5, -2. And if x is -0.25, that's going to give me a y value of -4. Okay, so as you can see, we are getting closer and closer to x equals 0. And so the next value I have is -0.01, basically -1/100th. Okay, so I'm getting really, really close to 0 at this point. And when I do 1 divided by this, I end up with a -100, which is not even on our scale here. Okay, so telling us that our function is basically just plummeting downwards. Okay. Now, if I think about what's happening as I go further to the negative side, so let's say I tried -100, I would have -1 over 100, which again is a very, very, very small value. And so on this side, I continue getting closer and closer to 0, okay, but not ever touching it. We don't have any x values that would allow for y to be 0. Let me go ahead and connect these here and over here. Okay. All right, so that's what's happening as we approach 0 from the left. Now let's see what happens after we pass 0. So again, I'm starting with a nice small number, 0.1. So 1 divided by 0.1 will give us 10. So again, really close to 0, but up here. If I let x equals 0.5, that gives me 4. So that's about here. And if x equals 0.5, I get 2. 1 gives me 1. 3 gives me 1/3. And 5 gives me 1/5. So again, my numbers are getting smaller and smaller and smaller, all of my output values. And I'm getting the same effect on the other side. So the graph goes up really high in that direction. And when it comes back around, again, gets really, really small and really, really close to the axis or to the y equals 0. So again, we have already talked about the fact that x can't be 0. So since x can't be 0, what I'm going to do is put a dashed line along x equals 0. And so what we are creating here is a vertical asymptote. All right, so we have a vertical asymptote at x equals 0. Okay, but we also saw that there is no input that will possibly give us an output of 0. And so again, we don't touch the y equals 0 either. And so I'm going to also draw in this horizontal asymptote. Okay, so there is the graphical image of 1 over x. All right, so more about asymptotes. All right, so these are basically just lines that the curve of our graph will approach as the graph heads towards infinity. Okay, so we've got 3 types. The first one, the vertical. And so if you remember the vertical, this has to do with what is not in the domain. Okay, so you can think of this one as coming from the denominator. Okay, the x terms not in the domain. Okay, now for the horizontal, this actually is what we would refer to as an end behavior asymptote, and we have 2 of those. So we're going to abbreviate end behavior asymptotes with EBA. And again, 2 of them. We've got horizontal asymptotes, which is like the one we just saw in the 1 over x. And we also have oblique asymptotes. Okay. So again, these are both types of end behavior asymptotes. The obliques are also known as slant asymptotes. So you'll hear those terms used interchangeably. And while this year we will talk about how to identify if it's an oblique or not, we are not actually going to solve for them or graph any of them. All of the work we do this year will be with horizontal asymptotes. All right. So more information about our end behavior asymptotes. Again, the end behavior asymptotes are either horizontal or oblique. Okay. So the graph will have at most one end behavior asymptote, and in order to determine what kind of end behavior asymptote we have, we are going to compare the degrees of the numerator and the denominator. So remember, the degree of the expression is based upon the highest exponent, the largest exponent in both the numerator and both the denominator. Okay, and again, it's the single one. We don't add them up together. We just strictly look at the highest degree of each. Okay, so if the degree of your denominator is bigger than the degree of the numerator, you get a horizontal asymptote at y equals 0. Okay, so again, if the bottom is bigger, and so an example of that would be, let's say we had f of x is equal to about an x minus 1 over an x squared plus 2. Okay. So in the numerator, we have a degree of 1 compared to in the denominator a degree of 2. So therefore, the degree of the denominator is bigger. Okay. And this one is what I would call big on bottom. And I'll say more about that in a minute. Okay. The other one, the degree of the top is bigger than the degree of the bottom. All right, so for this one, this would be like f of x is equal to x squared plus 2 over x plus 1. Okay. So again, the degree in the numerator is a 2 versus the degree in the denominator of 1. And so we get, for these, an oblique or slant asymptote, okay, but not a horizontal. So oblique or slant. And our last situation is if you have equal degree in both the numerator and the denominator. And if that's the case, you get a horizontal asymptote, and it occurs at y equals, and then what you do is take the coefficient of both the numerator and the denominator, the coefficients from the lead terms, and you divide those. Okay, so this would be something like f of x is equal to, let's say, 4x squared minus 3 all over 2x squared plus 1. Okay, so again, I have a degree 2 in the numerator and a degree 2 in the denominator. So exponents are the same. So we're going to take the coefficients of the lead terms. Right? So the lead term here is a 4. The lead term here is a 2. 4 divided by 2 is 2. So therefore, this function has a horizontal asymptote at y equals 2. So because this is a lot to remember, I use a little acronym, and I can't take credit for it. I had a student teach me this acronym many years ago, and I just really liked it, so I've kept it. All right, so in our first one, we're going to call this one a Bobo. And in the next one, we're going to call this a Botan. And the last one, we're going to say eats DC. All right, so let me put all of that together here because I make it into one statement. And so that statement is Bobo, Botan, eats DC. All right, so when I hear Bobo, it makes me think of a monkey. Somebody else told me a clown, and I also heard that it means silly, so in Spanish. So to me, yes, it is a silly name. So Bobo Botan eats DC kind of makes me picture a monkey making their way around Washington, D.C. and just eating everything. All right, so back to what does it mean? So the Bobo is a big on bottom. Big on bottom, and that O at the end is actually a 0, meaning we get a horizontal asymptote at y equals 0. Right. The Botan is a big on top. And the N on that means that there is no horizontal asymptote. So again, remember, if you're big on top, you end up getting a slant or oblique, which is not a horizontal. And the last one, which is kind of the long one, is an exponents are the same. And again, when the exponents are the same, we get a horizontal asymptote from dividing the coefficients. So that's what that DC is. Divide coefficients. Okay, so that is the acronym that has stuck with me. If you can think of something else, I would love for you to share it. So the other thing I want to mention is if you end up with the horizontal asymptote, what we're going to do is plug that in for our y, because again, it's a y equals, and see if the graph crosses it or not. Okay. If we were working on oblique asymptotes this year, we would do the same with that. However, that is something reserved for next year. So this year, we're only working with the horizontals. So the next thing I want to talk about are holes. Okay. So if you have a rational function, which can be simplified, then you get a hole in the graph where the original function had an x value that was undefined. Okay. So this is a very basic example here. We started with f of x equals x plus 1 over x minus 2, and with an x minus 2 in the numerator as well. And when you go to simplify this, right, we know that x minus 2 and x minus 2 divide out. And so what happens is the graph of our function is actually only going to look like what is left over. In this case, it's just a line with a slope of 1 and a y-intercept of 1. But we have to keep in mind that the original function did have an x minus 2 in the denominator, so x cannot be 2 because it is undefined at that point. Right. And so what happens is, again, our graph is going to look just like the simplified graph, except we have a point where it is undefined, and we indicate that point by creating a hole there. Okay. So again, we know x can't be 2, but if I were to plug 2 in to the simplified graph, we'd see that we get 3, the 0.23. And again, if you come back to the graph, we see, okay, at that 0.23, there is indeed a hole. There is a discontinuity there. Okay, so we're going to kind of take all this information and start bringing things together. So these first several examples that we're going to run through, we're not even going to create the graph of. I just want us to practice finding vertical asymptotes, finding the end behavior asymptotes, checking to see if we have a cross of our end behavior, checking for any holes, and then the last thing is we're going to state the domain of each function. Okay, so our first example is 1 over x minus 2. This is already simplified, and so there is nothing to divide out, and so I'm just going to start with vertical asymptote first. My vertical asymptote is x equals 2. Again, because x cannot be 2, because it would make the denominator 0. All right, our end behavior asymptote. So, again, we have to compare the degrees of the numerator and the denominator. So I notice that I have an x, this is basically to the first power in the denominator. I don't see a variable in the numerator. So technically, what is up here is an x to the 0. Okay. So now I can compare the 0 to the 1, and I see that means that my denominator is larger. I am bigger on bottom. Again, that's that bobo. And again, the O at the end represents the 0. We have a horizontal asymptote of y equals 0. All right, so since we have a horizontal asymptote, I want to check to see if the graph crosses that horizontal asymptote. And this will make more sense when we start to look at the image. For now, I just want to go through the process of it. So y equals 0, so that means I'm going to take the function and set it equal to 0. So that gives me 0 equals 1 over x minus 2. That denominator is going to divide out to 0, leaving me with 0 equals 1. Which is a false statement. And if we get a false statement, that means that this graph does not cross the asymptote. Okay, So next thing I want to address, do we have any holes? Well, we didn't simplify anything out of here, and if you don't simplify anything out, you cannot have a hole. So in the end, we only have one restriction on the domain. That restriction is x equals 2. So in interval notation, we're going from negative infinity to 2, and then picking up again from 2. Sorry, let me rewrite that. From 2 to infinity. All right. So for our next one, I've got 4x over x times x plus 2. First thing we do is look to see if we can simplify. And we see here, I have an x that will divide out an x here. And so this function simplifies to 4 over x plus 2. All right. So from there, I want to identify the vertical asymptote. Looking at the denominator of x plus 2 equal to 0 means that x equals negative 2 is the vertical asymptote. All right. The end behavior asymptote. So this is just like the one we just did previously. All right, there's a first degree down here. There's a 0 degree up here. So this is another case of big on bottom, or a bobo. So we have a horizontal asymptote at y equals 0. So checking for the crossing again. So as we saw earlier, if you divide both sides by that numerator, multiply, and to a 0, it's going to 0 out. Okay, sorry, I had to take a little pause there. I believe we left off at y is equal to 0 is the horizontal asymptote, so I want to set my equation equal to that and solve. And so the x plus 2 in that denominator is going to 0 out, leaving us with only 0 equals 4. Again, this is a false statement, and so this one does not cross. Okay. Okay, so the next thing we want to look at are, do we have any holes? And at the beginning, we did simplify x over x, which means we do have a hole at x equals 0. And we can go a little bit further by actually finding what that point is. So I'll take the f of 0, plug it in. I get 4 over 0 plus 2 is 2. And we get 2 there. So the hole is actually at the point 0, 2. Okay, so the last thing is the domain. And so we had 2 restrictions. Our restrictions, x couldn't be 0, and it can't be negative 2. So into interval notation means I'm going to go from negative infinity to negative 2, negative 2 to 0, and then 0 to infinity. All right. Our next one. So in most of the classes, I had you guys try this one on your own. So I'm just going to run through this pretty quickly. We cannot simplify this any further. So identifying the vertical asymptote, we get an x equals 0 because of the x squared in the denominator. Our end behavior asymptote, this one is, and exponents are the same, which is a divide coefficient. So again, that's because we have an x squared term in the numerator and an x squared term in the denominator. So we get a horizontal asymptote at y equals, the coefficients are 10 over 5. So y equals 2 is the horizontal asymptote. So again, I want to check for crossing, which means I'm going to set the equation equal to 2. And when I multiply the denominator over, that's going to give me a 10x squared on the left equal to 10x squared plus 3 on the right. My 10x squared terms will cancel each other out, leaving me with a 0 equals 3. Again, false statement, so this does not cross, and I'm going to go ahead and start abbreviating does not cross with a DNC. All right. Also want to check for holes. We did not simplify any terms out, so therefore no holes. And the only restriction we have on our domain is the 0. So in interval notation, that takes me negative infinity to 0, picking up again from 0 to infinity. The next one, some of you did move on and try that one on your own. And the first thing you notice is that the denominator can be factored. So we get 6x, oh sorry, that's a cube, all over, and then the denominator factors into x plus 4 and x minus 2. Okay. Nothing simplifies out of this, but now because it's factored, we can see that we have two vertical asymptotes this time. All right, we've got one at -4 and one at +2. Addressing our end behavior asymptotes, I have a degree 3 in the numerator and a degree 2 in the denominator. So this one is a big on top. That's a bottom. Okay, again, the n means that we have no horizontal asymptote. Okay. So no horizontal asymptote on this one. And since there's no horizontal asymptote, we're not going to check for any crossing. Again, keeping in mind that you will be doing this next year. All right, we didn't simplify anything out of this one, so therefore there are no holes. And again, our only restrictions are on those two vertical asymptotes. So we have a domain from -infinity to -4, from -4 to +2, and from +2 to infinity. All right. So in E, I've got x plus 2 times x minus 1 all over x plus 2. So first thing we want to notice is these two terms simplify out. In the end, our function is just x minus 1. All right. So with that in mind, we have no vertical asymptotes. Looking at the end behavior. All right, so this is like having x minus 1 over 1. So in this case, there's really nothing to compare here. So I guess you could say it is a big on top, I guess technically, which is a big on top. It's a bottom, so no horizontal asymptote. We did simplify the x plus 2 term, so we do have a hole at x equals -2. And we can figure out that exact point by plugging the -2 into the simplified equation. So -2 minus 1 gives us a -3. So this one here is a hole at -2, -3. All right, so the only domain restrictions we have are on that -2. So our interval notation is -infinity to -2, picking up again -2 to infinity. All right, so F, I'm not going to go through this one because I have it further down in a graphing example, and so all the information that we're going to obtain from that, we will also be obtaining for the graph, so we'll look at that one there. All right, so we're going to start with our graphing examples. All right, so just as we just talked about, find the vertical asymptotes first. We'll get those graphed. Then find your end behavior asymptote. Again, if it's an oblique, we won't worry about it. If it's a horizontal, we have to check to see if it crosses. Then we want to find the x-intercepts, plot those. Also, y-intercepts, plot those. Again, those are both things that you already know how to do. Identify any holes. If there are holes, get those plotted. And then the last thing is, in order to figure out what the graph is doing, is we're going to have to pick some test points. And when we say by the vertical section, so again, looking on every side of the vertical asymptotes and determining a point there so we can figure out where it's going. All right, so here's our first one. I've got x plus 2 over x minus 1. It's already in its simplified form. So first thing I'm going to identify is the vertical asymptote. So looking at the denominator, x minus 1, we know we have a vertical asymptote at x equals 1. So I'm going to sketch that in to my coordinate plane here. Right, there's my vertical asymptote. For my end behavior, again, compare the degrees of the numerator and the denominator. First degree here, first degree here. This is an exponents are the same. Divide coefficients rule. Oh, sorry, that should be a C, not a D. Divide coefficients. So again, that gives us a horizontal asymptote. I have a 1 for each of those, so 1 over 1, y equals 1. And I'm going to go ahead and sketch this in as well. Okay, and then we said if you do have a horizontal asymptote, check to see if the graph crosses it. So I'm going to set the equation equal to 1. So 1 equals x plus 2 over x minus 1. Multiplying the x minus 1 to both sides gives me an x minus 1 equals an x plus 2, which means those two x's will cancel out. I'm left with negative 1 equals 2, which is a false statement, so this does not cross. So next thing, I want to find my x-intercepts. So x-intercepts means you set y equal to 0. And so the denominator is going to 0 out when it gets multiplied over. So I'm only concerned with setting the numerator equal to 0. So 0 equals x plus 2, which means x is equal to negative 2. So we have an x-intercept at negative 2, 0. And I'm going to go ahead and plot that. All right. Checking for y-intercepts. That's when x is equal to 0. So I do f of 0, and I get 0 plus 2 over 0 minus 1, which is 2 over negative 1, which is negative 2. So our y-intercept is the point 0, negative 2, which I will plot right here. Okay, so we can already see that the graph should be connecting between these two. And then what happens is, again, the horizontal asymptote determines the end behavior, which means that the graph is going to have to continue on in the direction of the asymptote. And it's going to go close, but not touch it. And the same thing as it goes towards our vertical asymptote, just like we saw in our beginning example, it's going to sort of plummet down to negative infinity without touching the vertical asymptote. So now we know what is happening on the left side of the vertical asymptote. I need to find out what's happening on the right as well. So to find out what's happening on the right, what I'm going to do is pick a test point on the right. Okay. So I can't test x equals 1, again, because that's actually on the asymptote, so I'm going to test 2. And again, I could test 3 or 4, but 2, that should give me some smaller numbers. So 2 plus 2 is 4, 2 minus 1 is 1. That gives me 4, so again, I have a coordinate point at 2, 4. And so plotting that. All right, so I don't actually need any other points at this point because I know the end behavior tells me that as I go to positive infinity, I should be going towards the horizontal asymptote. And the other side can only be going from one direction, so it's going to go up towards the vertical asymptote. And there is our graph. We could talk about the domain and range. Here, I'll put that up here. The domain of this, again, the only restriction was on 1. So for domain, we'd go negative infinity to 1, union 1 to infinity. For the range, we don't have any values for y equals 1. So 1 is actually not in the range. So this one would be negative infinity to 1, union 1 to infinity. Here's our next one. X minus 3 over x squared minus 1. First thing I want to do is factor this. We get x minus 3 over x plus 1, x minus 1. So nothing simplifies out in this one. So I can just look at my denominator and I see I have vertical asymptotes, 2 of them here at negative 1 and positive 1. So I'm going to go ahead and sketch those in. All right, for the end behavior asymptotes, again, comparing the degree, let's see here, I've got one here, there's one here and one here. So it's actually a squared on the bottom and a first power on the numerator. So this one is a big on bottom, or a bobo, as I like to call it. So it's a horizontal asymptote at y equals 0. So I'm going to go ahead and draw that in. Okay, so we always want to see if it crosses the horizontal asymptote. So when I take this equation and I set it equal to 0, my denominator is going to 0 out, leaving me with 0 is equal to x minus 3, which means that x is equal to 3. So we know that we are crossing at the point 3, 0. So I'm going to go ahead and plot that. That's about there. And the nice thing about that one is that was also the x-intercept. So we kind of took care of 2 things at one time. So, all right, we should be happy when we take care of 2 things at once. Okay, so the next thing I want to look at is the y-intercept. And for the y-intercept, we're looking what happens when x equals 0. So f of 0 is, we get 0 minus 3, which is negative 3, and 0 minus 1, which is negative 1. We get a positive 3 here. I have a y-intercept of 0, 3. So that's about over here. Okay, we don't have any holes, so now it's a matter of putting this together. All right, if I'm looking at my middle section only, okay, the region between the two vertical asymptotes, between -1 and +1, okay, we've already established that we do have a point that the graph crosses the horizontal asymptote, except that crossing occurs out here on the other side of the asymptote, not in here, okay? Which means when I'm looking at this graph, it can't turn downward, okay? Because if it turned downward, it would mean that it would have to cross over the horizontal asymptote, and we've already established that it cannot do that here. So therefore, there's only one direction this graph can go, and that has to be in the upward direction. So both tails will go up towards positive infinity. Again, they'll approach those vertical asymptotes but not touch them. Okay, so now I want to know what is going on the right side of my graph. So after x equals 1. We've already established that we have a crossing at x equals 3, so I'm going to check and see what happens when I find f of 2. Okay, so f of 2 means 2 minus 3 is -1, and then we get 2 squared is 4, minus 1 is 3. Did I do that right? 2 minus 3, sorry, I did not do that right. I thought it looked funny. 2 minus 3 is -5. There we go. That looks better. Okay, so again, this is the coordinate point 2, -5, 3. So that's about over here and about over here. Doesn't need to be exact. Main thing is I know it's negative. So again, I know that my graph has to connect between here and here. We've already established that it crosses at this point. So usually what happens if it does cross, it tends to go up a little bit, but then it's going to bump right back down because remember, we've already sketched in this horizontal asymptote, which determines the end behavior. So again, this is the end behavior. So this graph goes through, usually bumps up, and then comes right back down, and then follows the horizontal asymptote. And this side just continues down, following the vertical asymptote. All right. So the next thing is, I have not addressed what's going on the left-hand side yet. So I'm going to pick a term over there. -2 sounds good. So if I plug in -2, I get -2 minus 3. Oh, I just realized I messed this one up. This is actually positive 2 minus 3 is -1. Sorry about that. I'm sure all of you caught that way earlier than I did. Okay, fix that. Alrighty, so this point is actually the -5/3, so this is -2, -5/3. All right, so -2, -5/3, somewhere down in here. And again, we've established that we don't have a crossing on this side, so we only have one direction we can go. It has to go this way towards the horizontal asymptote, and this tail has to go towards the vertical asymptote. And there's our finished picture. So if you want, you can put this into Desmos and get a better idea of exactly what the shape is. I think it's a kind of cool looking graph. It'll be more exact. And then just keep in mind, when you use software for the graphing, it will not plot the asymptotes for you. But you can see the lines just based upon where your end behavior is going. All right. I know some of the classes we got to this one and some we did not. So I'm going to run through here. First thing is to factor this. So our numerator factors into x plus 4, x minus 3. Our denominator factors into x minus 3, x plus 2, in which case the x minus 3's will divide out, leaving us with x plus 4 over x plus 2. So this is actually what our graph will look like. It'll look like x plus 4 over x plus 2. So now I can identify my vertical asymptote. X equals -2. I'm going to go ahead and plot that. Okay. Looking at our end behavior asymptote, I've got a degree 1 and a degree 1. This is the exponents are the same. Divide coefficients. So we get a horizontal asymptote at y equals +1. So I'll go ahead and plot that in. Okay, do we cross? If I set our simplified function equal to 1, I'm going to get x plus 2 on this side equals x plus 4. Our x's will divide out, leaving me with a false statement. This one does not cross. Okay, y-intercepts. Again, the denominator will zero out, so we're only looking at the numerator. So x plus 4 equals 0, which means x equals -4. So we have an x-intercept of -4, 0. All right. Y-intercept. What happens when we do f of 0? F of 0 gives us 4 over 2, just 2, so we have the point 0.04. So 0, that's about over here. Okay, so what's really nice about this one is we already have points established on each side of the vertical asymptote. We have already figured out that we do not cross, so there's really only one way for this picture to come together. From the left side, our graph will approach the horizontal asymptote from there and the vertical asymptote from here. And from the right side, the horizontal from here and the vertical from here. Okay. So the only other thing is we did simplify a term out. What term did we simplify? Remember, we did that x minus 3 up here. Well, that means that there is a hole in this one. So we have a hole at x equals +3. So that means if I come to x equals 3, which is about right here, I should have a little discontinuity here because this one point is undefined. So we'll put that in. And again, we can find that exact point by plugging into the simplified form. F of 3 is equal to 3 plus 4 is 7, and 3 plus 2 is 5. So 7 fifths. So again, our hole is at 3 7/5. Right. So if we were to discuss the domain and range here, we have two discontinuities for the domain. So we're going -infinity to -2, and then we go from -2 up to +3, and then 3 to infinity. Okay, so the range on this, we have a little more to consider this time. So we know that we have this asymptote that we don't cross. So we know that +1 is not in the range. So we go -infinity to +1. and then we pick up again at 1, but because we have this discontinuity here, which is at, we found that earlier, at our whole 7/5, so 1 to 7/5, and then we pick up again from 7/5 to infinity. So that one has a little more interesting range. Okay, so this is the example that I stated earlier. We weren't going to go through all the pieces because I put it into the graph. So we'll run through this one now. All right, first thing is, let's try to see if we can factor and simplify. So we get 3x squared plus 2 all over the denominator factors into x plus 5 and x minus 1. So nothing simplifies here, but I can see my vertical asymptote at x equals -5 and 1. So 2 vertical asymptotes, so 1, 2, 3, 4, 5 in the negative direction. I'll sketch that in. And 1 here. Okay, and so now look at our end behavior asymptotes. This one is, and exponents are the same, divide coefficients, so we get a horizontal asymptote at y is equal to 3. So I'll plot that in. All right, checking for crossing. If I set the left side equal to 3 and I multiply everything through, I'm going to get 3x squared plus 12x minus 15 is equal to 3x squared plus 2. So my 3x squares will divide out or cancel each other out, and then I get 12x is equal to 17 and x is equal to 17 over 2. Okay, so that means we do have a cross at 17 over 2 and 3. I should say that, the point 17 over 2, 3. Okay, so that's going to take us somewhere out here. Oh, that's not 2, that's 12, sorry. 17 over 12, so somewhere over here. Okay, x-intercepts, meaning I set y equal to 0. So again, this is not going to affect the denominator at all. It's just the numerator. So I do 3x squared plus 2 equals 0, which gives me 3x squared equal to -2, which gives me x squared is equal to -2 over 3. And we cannot do that. That's an imaginary number, so therefore there are no x-intercepts. All right. Finally, we have the y-intercept. So f of 0 is equal to, I'd get a 0 plus 2 is 2, and then a -5. So we have the point 0, -2/5. Okay, so about somewhere over here. All right, so this is similar to the one we did earlier when we had 2 vertical asymptotes. So a couple things here. In between my 2 vertical asymptotes, we know we don't cross, but we also know that we don't have an x-intercept. So without an x-intercept, there is no way for this graph to go up and touch the x-axis. So again, I don't know exactly where this turns. You can put this into Desmos or something to see, but there's only one direction for this graph to go, and that is in the downward. So we're going down there towards the vertical asymptotes. Okay, so on the right-hand side, again, I know I have a cross, but I don't know if I'm coming from above or below, and so I need to test a point. And let's see. Let's test, how about 2? All right, if we plug in f of 2. All right, so if I plug in f of 2, I'll get 2 squared is 4 times 3 is 12 plus 2 is 14. And in the denominator, let's see, we get 2 plus 5 is 7. 2 minus 1 is 1, and so we get 2, the 0.22. So that's going to be about over here. So that tells me that the graph has to be coming this direction. And again, since it crossed through, I know there's a little bump, but again, the end behavior will determine where it goes. So it will turn back towards the horizontal asymptote, and this one can only go towards the vertical. All right, last thing is what is happening on the left-hand side. So I'm going to plug in -6. That's on the left-hand side there. Okay, so when I plug in -6, -6 squared is positive 36. Multiplied by 3 is positive. I'm not even getting exact numbers here. I get a positive in the numerator. And if I plug in -6 plus 5, that's also a positive. And if I plug in -6 minus 1, that's going to give me a -7. Okay. Oh, actually I realized I just made a little arithmetic error there. Let me fix that. Actually, if I have -6 plus 5, that's a negative. Okay, that makes more sense. Now I have a positive divided by a negative times a negative, which will turn into a positive. So this is a positive divided by a positive. That's a positive. And again, I'm not actually calculating this whole thing out because those numbers are quite large. What I was trying to figure out is, am I going to be far up above? And I was, because those were going to come out to be big numbers. So I'm up here somewhere. And there is the left side of the graph. All right, so again, this one's a pretty interesting looking graph if you want to plug it into Desmos and see. Again, it won't plot the asymptotes for you, but you can kind of see where they are just based upon where the graph starts to sort of, it looks like it's straightening out. Okay. Okay, so our last few examples that we're going to do involve finding the rational function based upon the attributes that are given. Okay. So again, we know we are writing a rational function, so I'm going to set this up as an f of x equals and go ahead and create my little fraction bar here. Okay, so the information given to us. First it says a vertical asymptote at x equals 1. So knowing that vertical asymptotes come from the denominator, okay, then we know the expression that creates x equals 1 is x minus 1, so we get an x minus 1 in the denominator. Okay. Next thing, horizontal asymptote at y equals 3. So in order to have an asymptote horizontal that's not equal to 0, that would mean that the exponents had to be the same, and you would divide the coefficients. And in dividing the coefficients, you should simplify to 3, or you could also think of that as 3 over 1, meaning we'll have a 3 in the numerator, and we won't worry about putting a 1 in the denominator. The next part, x-intercept of 5, 0. Okay, and if you recall, the x-intercepts are created or found when you set y equal to 0 and you solve. So therefore the denominator is irrelevant to it, and you're just going to look at the numerator. Right? And so 5 would come from the expression x minus 5, and again comes from the numerator. Okay, so now we have x to the first over x to the first. Exponents are the same. If we divide the coefficients, we'll get 3 over 1, so we are basically done with this one. Okay, for the next one, again, it's a rational function. So I have f of x equals, I'm going to make my fraction bar. So the first attribute they told us was there's a whole at x equals 2. So in order to have a whole, it means that we had to have a term divide out. So x equals 2 would come from the expression x minus 2, and therefore we'd have to have that both in the numerator and in the denominator in order to divide out. We also have a vertical asymptote at x equals 4. And again, vertical asymptotes come from the denominator, and that would come from the expression x minus 4. Next one, we have x-intercepts at -1 and 0, and again the x-intercepts are going to come from the numerator, so -1 would come from the expression x plus 1, and 5 would come from the expression x minus 5. Okay. And it says we have an oblique asymptote, and if we look at this, this is currently an x cubed in the numerator and an x squared in the denominator. So this is a big on top, and so this would give us an oblique asymptote. Here are a couple more. We have, again, we're writing a rational function, so I'm going to set this up with my fraction bar. Vertical asymptote at x equals 2, so that means the denominator will have an x minus 2. Horizontal asymptote at y equals 3. Again, that means the exponents have to be the same, and we divide coefficients, so like the previous one, 3 over 1, so I'm going to put a 3 in the numerator and not worry about the denominator, or the 1 in the denominator, and a 0 at x equals -5. Well, what does that mean to be a 0 at x -5? Well, that's just the x-intercept again. So that's the point -5, 0, which would come from the expression x plus 5, and again, those come from the numerator. Okay. And again, our exponents, the powers match in both the numerator and the denominator, which matches the information we got regarding horizontal asymptote. Okay, this next one, a little bit different here, but again, we're going to set it up the same way. I have f of x equal to fraction bar. Vertical asymptotes at x equals 3 and -3. So again, those come from the denominator, from x plus 3 and x minus 3. We have a horizontal asymptote at -4, which means we must have a -4 in the numerator, again, because this would be plus 1. Now here's the tricky part of this one. It says there is no x-intercept. So there's a couple things we have to keep in mind. If this has a horizontal asymptote of -4, that means we had to have a division of coefficients. So exponents would have to be the same. So I know I need to have some sort of an x squared up here because I have an x squared in the denominator. So next thing I have to consider is we would be setting this numerator equal to 0 and solving for x. So if I have -4x squared and I'm trying to set it equal to 0, if I solve it the way it is, I'm going to get x equals 0, which should mean we have an x-intercept of x of 0. And we don't want an intercept. So we have to think of what is it we can do so that we would not be able to solve for x. So if you notice, x is squared, which means at some point we will have to take the square root of it. And keep in mind, we cannot take the square root of a negative number, not at least graphically. Of course, we know we can get imaginary numbers, but it's not going to work for our graph here. So if I'm dividing by -4 in the end, I need to have a positive value on the other side. So let's say, I'm just going to pick a value here. What if I just do -5 on this side? Okay. So if I go to solve for this now, that would give me -4x squared equal to 5. And then I would divide both sides by -4. That would give us x squared, oops, sorry, I forgot the negative there, is equal to -5/4. And at this point, I can't take the square root of this because it is negative, which means we would not be able to solve, and that would give us no x-intercept. So -5 up here would work, and actually there's a whole infinite number of terms we could put in there that would make this work for us as well. All right, so the rest of the problems are all you tries. I'm not going to talk through them, but I am going to go ahead and post what the final answers look like. Okay, so here are the final you tries that we didn't have time to work on in class. So there's A, there's B, there's C, D, and E. If you're still having trouble with these, please don't hesitate to ask questions. Hopefully you'll find as you just get a couple of them done, it starts getting faster and starts pulling together better.